This video lecture is meant to give you more detailed information about the quantum numbers that we've been using as we've been writing orbital diagrams and electron configurations. These are all based on the quantum mechanical model of the atom that we have currently, which was developed in 1926 by Erwin Schrödinger and Werner Heisenberg. And they developed a set of equations that describe the behavior of an electron. And this is the mathematical formula for that, and you don't need to worry. That is not something you're responsible for, but I thought it would be interesting to show you the mathematical equation, at least a part of a wave function. Schrödinger and Heisenberg believed that electrons are found in discrete energy levels, as Bohr did. However, the electrons don't move around the nucleus in a fixed orbit. They are actually clouds of probability of finding the electron, which led to what we now call the modern quantum theory. So the modern atomic theory that we currently subscribe to is that orbitals describe the three-dimensional space that electrons occupy. So we've gone from this orbital, this orbit notation, which was what Bohr believed, where we had the electrons circling the nucleus like planets orbit the sun, to now an orbital or a cloud of probability of finding electrons. The location of an electron can only be described by probability. So for example, if you were to have a little tracking device on you throughout the day, there would be a high probability that your parents would find you closer to Hill Murray on a school day than away and off campus or other places. However, once the school day ended, then we could track you and find that you would go somewhere else. So there's a higher likelihood that you'd be at Hill Murray during a school day than not. Orbitals give shapes to the atom, and here are some different shapes here. I'm going to go into a little bit more depth into as I talk a little bit more about these, but these are the shapes just to kind of give you an idea of what the orbitals look like. And these properties allow us to describe electrons in terms of their energy and position. Quantum mechanics might sound a little scary, but if you think of it this way, it's kind of like the address of an electron. Quantum numbers allow us to pinpoint the location of one electron, or the general location of one electron. It's kind of like if you've ever mailed a letter, you need to have the state, the city, the street number, and the house number of where somebody lives. Well, electrons are identified the same way, only it's not like writing out an address on an envelope. There are special names for the quantum numbers, and those names are the principal quantum number, the angular quantum number, the magnetic quantum number, and the spin quantum number. These tell us the distance the electron is away from the nucleus, what shape orbital they're in, the magnetic position that they're in, and whether or not their spin is clockwise or counterclockwise. So these quantum numbers describe the orbital that's occupied by a specific electron. Let's take a look at what each of these four quantum numbers represents and then do some examples with these. The first quantum number is called the principal quantum number, and it's denoted by the lowercase letter n. It indicates the main energy level that's occupied by the electron, or the distance away from the nucleus. The values of n can only be positive integers, so starting at principal energy level number 1, 2, 3, 4, etc. And it goes up to 7 because that represents the period on the periodic table that the particular element is in. Now, things get a little interesting when we look at elements in the transition and intertransition metals, which we've seen in class. But for the most part, when we look at the main group elements, the principal quantum number indicates the row, or the period, that that particular element is in. The second quantum number is the angular momentum, which is indicated by a lowercase letter L. And what this does is indicates the shape of the orbital, so the actual three-dimensional space where the probability of finding an electron is the greatest. And it is a sublevel of n. This is designated as S, P, D, or F. The value of the angular momentum changes depending on the type of orbital you have. So if you have an S orbital, you have an angular momentum number or value of 0. If you have a P orbital that has an angular momentum value of 1, D has a value of 2, and F has a value of 3. You probably are wondering, where do the S, P, and D, F come from? Well, S comes from the word sharp, P principal, D diffuse, and F fundamental. These words were first used by spectroscopists to define the qualities of certain spectral lines. Later it was discovered that these qualities were related to the sublevel structure of the electron arrangement, so these letters were retained. And here's what those orbitals actually look like. So an S sublevel is actually spherically shaped. There's one way to arrange that in space, so one orbital. That's why we were drawing one box in our orbital diagrams. And an S sublevel can hold 2 electrons, as we saw when we were drawing our orbital diagrams. The P sublevel is peanut-shaped or dumbbell-shaped. There are 3 ways to arrange the P orbitals within 3 dimensions, and that's on the 3 different axes. The P sublevel can hold a maximum of 6 electrons. The D sublevel is double peanut-shaped, has 5 orbitals, and holds 10 electrons. And the F sublevel is flower-shaped, has 7 orbitals, and holds 14 electrons. As we were doing the orbital diagrams, I was hoping that you noticed the patterns. I've tried to point those out in class. And as you can see, it's very neatly ties into how the periodic table is arranged as well. The third quantum number is the orbital quantum number, designated as M sub L. That indicates the orbital the electron is located in. The center orbital is always designated as orbital 0, and it has values from negative L to positive L. An S sublevel has only one designation, so that orbital has an orbital quantum number, M sub L, of 0. The P sublevel has 3 arrangements in space, and so this center box here is the 0 point, kind of like a number line, and then you branch outward from that. So to the left of the number line is negative, left of the 0 on a number line is negative, and then to the right of the number line you'll have positive values. For a D sublevel, again the 0 will be in the middle. We have negative 1, negative 2, positive 1, positive 2. And then for an F sublevel, these are the positions that you would have. So again, 0 is the center, and then you move outward like you would on a number line. And what this quantum number tells us is what position the electron that you're interested in is holding within your orbital diagram. And the last quantum number is the spin quantum number, designated as M sub S. That indicates the spin of the electron, whether you have a positive 1/2, that's an upward spin or clockwise, or a negative 1/2, down one spin or counterclockwise. And that's denoted by whether the arrow that we've drawn in the orbital diagram is up or down. So let's put this all together and see what this means for a particular electron in carbon. Alright, so here I have the orbital diagram drawn out for carbon, and let's take a look at this particular electron right here. Okay, so what we want to do is try to write out the address or the quantum numbers for that particular electron. So what I've done is I've listed out what the 4 quantum number designations are, and we will go ahead and figure out how to fill this out. Alright, so N is our principal quantum number. That's the energy level that we're in, and we find that by looking at this right here. So 2p, the 2 tells us what energy level we're on. So the principal quantum number for carbon for this particular electron is 2. Right? L is the shape of the orbital. And we are in a p orbital. So for p orbitals, L is equal to 1. M sub L was the position on the number line. So remember, it was zeros in the middle, positive ones on the right, negative ones on the left. This particular electron we're looking at is in the negative 1 spot. And then M sub S is the spin of the electron. And this particular electron happens to be pointing up, so the spin is positive 1/2. So this is the electron address, or the quantum numbers, for this particular electron in carbon. Here's our next example. We have the orbital diagram of boron drawn here, and I've selected the second electron of boron to take a look at. So our first quantum number is N, and that's the principal energy level we're on. For this particular one, we're here, and that's in the first energy level, so N is equal to 1. L is the type of orbital, so we have an s orbital for our shape. That corresponds to 0. That goes up from 0, 1, 2, 3, S, P, D, F. M sub L, well, there's only one way to draw an s orbital because they are spherical, and so that is the 0 in the number line, so this is a 0. And then M sub S, that's whether it's up or down, and this is a negative 1/2. And for our last problem, here I have the orbital diagram of neon, and I've given you the address for a particular electron in neon. What I'd like you to do is to figure out what electron am I trying to describe. So pause this right now and see if you can figure it out. Did you pause it? If not, pause it. I want you to work on it. Alright, I'm going to walk you through it. N is equal to 2, so that's our energy level. So that means we're looking at these two possibilities here. L is equal to 1. Well, that throws the S out because that would be a 0. M sub L, positive 1. This is 0, negative 1, positive 1. So now we're in that box. And positive 1/2. So here is the electron that we were trying to solve this problem for. Did you get it right? If you did, congrats. If not, review. See if you can figure it out. And if you're still stumped, ask me in class. We're going to do lots of these over the next few days. Thanks for watching.